Okay, so today's topic is the last topic of this unit on the atmosphere, and it's an important one. It's actually something you've already basically studied without realizing it when you completed while working at least, on the assignment that's due later this week with the pressure differences between Darwin and Tahiti and the movement of warm water. The phenomenon is known as INSO, or El Nino Southern Oscillation, and it is a very major aspect of the global environment because it's responsible for changes in climate across the planet that occur on a periodic basis. So let's just see how it works. So the term El Nino refers to a warming of the waters off the coast of Peru in particular, but really all of the eastern Pacific basin. The water there is usually fairly cold, but what happens is every 3 to 7 years or so, warm water arrives off the coast of the Americas and spreads northward and southwards from the equatorial regions. And it really changes the climate and the fish productivity. It changes everything, really, not just in the Americas, but across the planet, because where there's warm water, there's convection, and where there's convection, there's winds, there's weather. So it changes everything. Now, uh, basically, the term El Nino, for those of you who take Spanish, means, I think in Spanish, it means something like little boy or little baby boy. Uh, and it was a term that was first used by the Peruvian fishermen. Now, the waters off the coast of Peru are normally highly, highly productive, the most productive ocean waters on the planet. And so the fishermen there enjoy, a very robust industry. But what they notice is that every, say, 2, 3, 7 years, something like that, uh, the water would get foggy, it would get warm, the fish would go away, their industry would collapse. And so when they noticed this warm water coming in, making fog, they refer to it as El Nino because it tended to arrive close to Christmas time. So it was referenced to the baby Jesus. Now, why is it that Peru normally has such great fishing? Well, it has to do with a phenomenon known as upwelling. And it's a little bit complicated. I'm going to try to simplify it a bit, but basically what happens is when winds blow along the shore, so that you have the Andes Mountains here, winds get forced along the shore. And when they do that, it causes a movement of water offshore. Let's not worry about why. It's complicated, as I said. But basically, the ultimate thing that happens here is water gets moved offshore. Well, when you move water offshore, water has to come and take its place. And the water that takes its place is this cold water from down below. Now, if you think about it, deep water should be high in nutrients because organisms that live up in the photic zone where there's light and there's photosynthesis, there's the upper 100 meters or so of water have a lot of life in them. And as these things die, they settle down to the bottom. And so the nitrogen and phosphorus in their bodies as they die just ends up in this cold, dark, low oxygen water that's deep in the oceans. And normally it doesn't have much of an opportunity to come to the surface except where we have upwelling. And so what happens is, as this water moves offshore, deep water comes up from below, keeping the coast here normally very cold, but highly productive because when these nutrients reach the surface, now suddenly there's light, there's photosynthesis, and the plankton goes crazy because they have all these nutrients with which to build cells. So there's a huge uh, explosion of primary productivity, and then that leads to consumers growing, and so you end up with lots and lots of fish, all kinds of sea life, bird life. Is just a very, very high productivity area of the ocean, courtesy of this upwelling, bringing up nutrients from below. Now, in normal years, what happens is this: winds are pushing, the trade winds are pushing warm equatorial water across the Pacific Ocean. We talked about those currents. Well, what happens is you end up with a lot of water pooling up over here, and we call it the West Pacific Warm Water Pool. And so it forms off of Australia and the Philippines and the other archipelagos in this region. And so the trade winds are basically holding this warm water here. So believe it or not, so much warm water gets pushed across. If you recall, we talked about the countercurrent. The sea level on this side of the Pacific, on the west side of the Pacific, is about half a meter higher than it is on the east side of the Pacific. And so it happens in normal years. We have upwelling happening here. We have warm water push over here with this deep warm layer here, and sea level is higher here than it is over here. So we have this 150-meter deep pool of warm water that's a little bit higher in sea level than it is over here, and it's held in place by these strong winds. Now, this thing is these winds are made stronger by a thing known as the Walker circulation pattern. Let's dive into that a little bit. So basically, we already know about that the north south Hadley cell that happens. Air rises at the equator and sinks at 30 degrees, and because of the Coriolis effect, it makes the trade winds. But what happens is when I get a lot of warm water here, I get a lot of convection here, more convection here than I get here. Remember, convection is just caused by uneven heating of the Earth's surface. So what happens is I have rising water here, which, by the way, contributes to the Asian monsoon. Basically, this is the source. This warm water is the source of the Asian monsoon. But then I have water sinking in the eastern part of the Pacific and then moving to the west. So basically, this reinforces the trade winds. So this causes the trade winds to be very, very strong because of this. Instead of a north-south, we have an east-west circulation pattern established because of the warm water here and the cold water here. Yeah, we just okay. So basically, raising, water, air going up here makes low pressure, air sinking here makes high pressure, and that's what causes this Walker circulation to be so strong. Um, we already did this, but one thing I want to point out is this is known as a positive feedback loop. So a positive feedback loop basically is this. Anytime you have a system in which the outcome of a change increases the rate or magnitude of that same change occurring, we call that a positive feedback loop. So in this case, what happens is as as because I have warm water here, I get convection here, and then that causes the pressure to be higher here and lower here, which causes the trade winds to be stronger. Well, by making the trade winds stronger, I move even more warm water across, which makes the convection even stronger, which makes the winds even stronger, which moves even more water across, which makes even more convection. So that's what we call a positive feedback loop. It makes itself stronger. Now, for reasons that we still don't really understand that well, every 2 to 7 years, there's a shift in air pressure called the Southern Oscillation, which is what your assignment was about. So, under normal conditions, what we find is there's low pressure in Darwin, where the warm pool is established, and there's higher pressure here in Tahiti. And that's just a convenient place to measure it. Okay, and so we find is there's higher pressure here from that Walker cell. Well, what happens is every 2 to 7 years, there's a shift that occurs. And what happens is uh, the pressure drifts over this way. All right. So what happens is warm water starts moving up here instead, and we get a shift in pressure, and the shift in pressure basically causes winds to start blowing the other way. The pressure moves from being low in Darwin to low in Tahiti and high in Darwin, and that basically breaks up this Walker cell. And so what happens? We actually get trade winds blowing, or rather winds rather blowing opposite of the trade winds, blowing eastward across the Pacific, moving this warm water in an eastward direction, which is what you saw in your assignment. This also serves to weaken these trade winds, so we're pushing less warm water to the west, and the water that's here is coming back over. And not only that, don't forget that the sea level is higher over here than it is over here, so that further aids in the flow of moving this water back across. And so we find as the trade winds weaken, this warm water moves back across, triggering an event known as El Nino. So in an El Nino, what happens is because there's no strong winds to hold it in place, this warm pool begins to flow downhill, and there's also the subsequent reversal of the movement of air. It's now blowing in this direction because the pressure is now high in Darwin and low in Tahiti. And that starts to just push all this warm water that's been building up here for 2 to 7 years, it pushes it back across, and it ends up spreading across the Eastern Pacific. Well, when that happens, it's going to have a lot of consequences as far as the world's weather goes. So basically, here's what we see. Here is under normal conditions. Here's under El Nino conditions. So under El Nino conditions, what's going to happen is now we're going to have, instead of air sinking here and having high pressure, we're going to have low pressure here. We're going to get rains in places where we don't usually get it. We're going to end up with drier than normal conditions in Australia. warm winters here. I mean, it changes the whole planet, all over the planet. There'll be parts of Africa that have drought. There'll be parts of Asia that have drought. There'll be floods in parts of the Americas. It just changes the complete distribution of energy, wind, and water across our planet. It's just a major shift in where the energy is distributed. All right. So here's a sort of a cross-sectional view of it. So under normal conditions, we see the Walker cell. We have air rising over Darwin and sinking over around Tahiti. All right. And we see that this also feeds into other patterns here. Okay. Here we have our monsoon occurring as a result of this. But then what happens is now in El Nino conditions, what happens is now the air is rising in the mid Pacific. So it's sinking here. We're not getting the monsoons. We're getting really dry periods in Australia. We're getting really dry conditions here in the Amazon. We're getting wet conditions here in America. We're getting floods in Africa. So you see, it just completely disrupts the entire uh, uh, circulation of air and moisture on planet Earth. And I'll skip this one. This one just shows you the different things that can happen here. It just gives you a sense of how things are different during these events. I guess I probably shouldn't have put that one as kind of a confusing slide. But basically, you should know that the effects of the El Nino are a weakening of the Asian monsoon, drought conditions in Africa and Australia, and then we get high rainfall in parts of North Africa, the southern US, and Argentina. There's also a thing called La Nina, and we'll finish with this. So La Nina is basically the opposite of El Nino. It is, for a reason we don't understand, there's a deepening of the low pressure here and a strengthening of the high pressure here. So it strengthens the trade winds and pushes even more water and makes this warm pool even warmer than normal and makes the water here colder than normal. And that too has consequences. It's not quite as extreme, but it is noticeable, especially over here in the western part of the Pacific. So what happens here is we tend to get a lot more rainfall with the Asian monsoon. Often this involves flooding in Australia because it's a fairly dry continent norm because a lot of rain. We get increased rainfall in Africa and Brazil, and drier conditions in the eastern part of the Pacific, including the United States and South America, and this leads to increased forest fires. Okay, so that's El Nino, La Nina, and INSO. I know it's a lot to digest, but I think we got a handle on it, and now we got to start getting ready for our second test of the year.